afternoon. Today's video is on static electricity. The first thing I want you to do, though, is to review the acronym WISE, which, of course, if you remember from the previous video, means 1. Watch, 2. Imagine, 3. Summarize, and 4. Evaluate. You're going to watch, imagine, summarize, and then evaluate your learning. So, to begin, we're going to first review the Bohr-Rutherford model of the atom. To move around, if you remember, an atom is made up of protons, neutrons, and they make up nucleus and electrons, which are these little guys orbiting the nucleus. Right? Now, one of the things we learned in chemistry was that the subatomic particles, like protons, also possess an electric charge. Protons and electrons possess an electric charge. So, what's an electric charge? So, the first thing we have to ask ourselves is, what is electric charge? Electric force is one of the four fundamental forces of nature. Any charged particle gives off an electric force in the form of these field lines that essentially go off to infinity. But of course, as you get farther and farther away from the source, the amount of force gets weaker and weaker. But protons have a positive version of this force, while electrons have a negative version of this force. The electrostatic law states that like charges repel and opposites attract. And of course, you've all experienced this on a very cold, dry day. If you pull a sweater over your head very quickly, this is what happens to your hair. Look at this little girl. She's just pulled her sweater off on a nice dry day, and of course what's happening here is that her strands of hair all have extra electrons on them, are negatively charged, and so they're repelling each other and standing out in this really frizzy way. And we can simulate that in a lab using a Van de Graaff generator, and if we can get... Now, of course, electric charge comes in two forms. The one you're most familiar with, of course, is current electricity. Current electricity, this is electricity carried by charged particles, either electrons or ions. But to begin this unit, we're going to talk about static electricity, which is electricity that does not move that much. But as we're going to see in the subsequent demonstration, static electricity does in fact move. Now, static electricity occurs whenever there's an imbalance between two charged objects. As you can see with this gentleman here, there's an imbalance between the static charge on the balloons and the static charge on his head. Thus, following the law of electrostatic induction, electrostatic attraction, the balloons stick to the man's head. And we can probably assume that the balloons, for reasons you'll see later, have a negative charge, and his hair has a net positive charge. And he doesn't look very happy about this. There are essentially three methods of charging an object electrostatically. The first two are examples of what's called electrostatic conduction, which is whatever occurs when two objects with different charges on them come into contact. So the first form is charging by contact. Rotate this, orient it. This is an example of a pith ball electroscope. So I've go over. This is a pith ball electroscope. It's a little pith ball. An electroscope is a device that can be used to measure electrostatic charge. This is a big plastic tube. You can make noise with it. And this is a piece of fur. What can happen is the fur generally has a weaker hold on its electrons than the plastic. And so when I rub the fur, you're going to get a net buildup of electrons on its surface. So when I approach the pith ball, it will stick to it and the electrons will jump from the plastic to the pith ball. That's charging by contact. Contact again. Now, of course, what I'm demonstrating when I'm charging the plastic rod by rubbing it continuously like this is the second form, which is called charging by friction. Now, the third form is called charging by induction, and it's a little bit more complicated. And to demonstrate charging by induction, I have to use a different piece of equipment. So I'll pull up my document camera again, and I'll move the pith ball electroscope, and in its place, you'll see something called a metal leaf electroscope. In a metal leaf electroscope, this little needle, plastic needle in here, attached to a piece of metal that runs up to a conducting plate at the top. And this metal needle is precariously balanced in a saddle. So we have our metal leaf electroscope. And I'm going to demonstrate, first I'm going to demonstrate charge transfer by friction. So I'm rubbing the plastic tube with my fur, my fake fur. No animals were killed in this demonstration. And I'm going to demonstrate electromagnetic induction, which is the electric field force operating on this metal object through space without touching. So as I bring plastic tube close, here you go. I'm going to ground it, and this should allow the needles to return to their zero position. What's happening is, I'm not touching it, but the electric field is actually causing electrons to move from the metal disc at the top down through the metal wire, the metal saddle that's holding the needle, and transferring to the needle. So the needle becomes negatively charged, the plates are negatively charged, and they repel each other. So essentially what happens is the metal leaf electroscope starts out in this situation with a balance of positive and negative charges throughout the metal. But as I bring the negatively charged rod towards it, the law of electrostatic attraction means that all the electrons in the upper part are going to run this way and create a net imbalance of negative charges down here. And so the two metal leaves will repel each other. Now, if you pull the rod away, what should happen is the electron should move back up and the normal situation should return. Materials can be divided into two basic categories. There are conductors and insulators. Conductors are materials like copper that allow for the free flow of electrons, generally from the valence shell. And metals, as you remember, don't tend to have full valence shells, and this allows electrons to move around between them. And insulators like rubber that don't. Their valence shells are generally involved in covalent bonding, and it does not allow for a lot of free electron movement. Now, tomorrow you're going to study something called, we're going to examine in a lab, something called the electrostatic series. And that's a way of ranking materials on their ability to attract or to donate electrons to other materials. And there'll be a short clicker quiz based on the material we've covered today. So make sure you watch this and understand it, and we'll have a lot of fun in the lab tomorrow.